let's take a look at section 5.5. So we talked about derivatives of exponential functions. So now we're going to look at derivatives of logarithmic functions. So again, we start out with a fact here. So we know for our ln of x, the derivative is 1 over x. Okay, now we have to include the absolute value bars here because if you remember from previous sections, we can only take the logarithm or the natural logarithm of a positive number. So let's take a look at a couple of the examples here. So here's my first function I'd like to differentiate. So the first thing I see is a product. So I'm going to set up my template for the product rule and then fill these bubbles in. So derivative of the first, 2x, times the second, plus derivative of the second, so I know derivative of that ln of x is 1 over x. Now we're assuming that the ln of x is defined here. And then times the first. So pretty easy. Let me just see if I can simplify it. I guess it would look like that. So I could leave it like that, or I guess I could factor the x out as a GCF. Either way. Okay, number 2. First thing I see here is a quotient. So I set up my quotient rule for bubbles, negative in the middle, the denominator squared. Okay, derivative of the top times the bottom, derivative of the bottom times the top. And then I see if I can simplify it all. X squared minus 3x squared ln of x. Okay, so then let's see, anything else? So I guess I can factor the x squared out of the numerator because that way I can cancel with the denominator. So 1 minus 3 ln of x over x to the 4th. Not too bad. Okay, number 3 looks like a chain rule. Okay, so first I look at the outer function, so that's an ln. So the derivative of that is 1 over the argument. Then times the derivative of the inner function. So let's see, that would be what? 6x squared plus 2x minus 3. Okay, number 4. Looks a little more interesting. So that one I have a couple options. So I guess I could use the chain rule. I'll be using the chain rule because I have, an outer piece and an inner piece. Then I would have to use the product rule for that guy. Then I guess I would be using the chain rule somewhere again for that guy. So I could do that. Seems like a lot of work. So what about another idea? So you see how here I have the log of a product multiplication here. Remember that rule? If I have the log of a product, I can break that up as the sum of 2 logs, sum of the log of each factor. So what if I use that rule? So what if I use that log property first? That's going to simplify my life quite a bit because it's actually I'm not even differentiating yet. I'm just taking g of x And I'm saying, well, can't I use the log property that I wrote below there to break that up as the sum of two logs, like so? Let me see what else I can do with log properties. Remember that rule that says I can bring this exponent down to the front? Maybe I should do that. Can't do anything with this first factor because that exponent's not on the whole argument. Could do that. So this is still g of x. So now let me look at finding the derivative. Okay, so then I'm using the chain rule, but this is a lot simpler than what we were looking at above. So, okay, outer function derivative of ln is 1 over the argument, but then times the derivative of the inside, 6x. Okay, again, I guess here it's going to be chain rule. Okay, derivative of the ln is 1 over the argument times the derivative of the argument. So let's see, multiply straight across, 6x over 3x squared plus 2. Okay, 5 times 4, 20x cubed over x to the 4th minus 1. I don't know, should I do an LCD? So kind of thinking, what will this look like if I do an LCD here? Try to combine these. So I'd be multiplying x to the 4th minus 1, and this one by 3x squared plus 2. LCD. So let's see, what would that give me? So I'm distributing, right? That'd be 6x to the 5th minus 6x. Okay, and then over here, same thing, I'm distributing this guy. Plus 60x to the 5th plus 40x cubed. And then I'll leave the denominator, how about? Just curious if we'll get any like terms or not. Oh, I guess so. So let's see, 66x to the 5th plus 40x cubed minus 6x's. And then I'll just leave that denominator. It's already factored. So how does that look? Sounds a little longer. Not terrible though. Here's another one with a product. So again, when I'm looking at this guy, first thing I see is I have that ln of a product. So I think I'm going to break that up using that log property that we talked about. In what section was that? 5.2? I think so. Okay. So then so far, again, I'm not actually differentiating, just breaking up the logarithm using log property. So I'm still just working with the function itself, not the derivative. Okay, now again, I can bring this exponent down as a multiplier. Oh, I guess also this one, huh? So then 3 ln of x plus x squared ln of e. Okay, and then what do we know about ln of e? Remember, ln of e is the same as log base e of e. So that's saying e to what power is e itself? The answer is 1, right? So actually this whole function then just turns into 3 ln of x plus x squared. So again, I haven't actually found the derivative yet. That's just simplifying the function using log properties. So now let me look at actually differentiating. It's actually going to be really easy now. So 3 times 1 over x plus 2x. That was super easy. Oh, I don't know. I think I'd do an LCD. So what does that turn out to be? 3 plus 2x squared over x. That's a cool one. Okay, what do I see with this one? First thing I see is another log property. Remember, when I have a division inside a log, I can break that up as a subtraction of 2 logs. The log of the top minus the log of the bottom. So that's the first thing I see. So again here, I'm not actually differentiating in the first step. I'm using the log property that says since I have a quotient inside of the log, I can break this up as the log of the top minus the log of the bottom. Then it's going to actually be really easy again to differentiate. Okay, I guess I need the chain rule here, but it's an easy one. So derivative of ln is 1 over the argument. But then times the derivative of the argument, right? The derivative of 3x is just 3. Okay, now minus, okay, chain rule again, but this one's even easier. So derivative of ln, I have 1 over the argument. But then the argument, derivative of x minus 2 is just 1, so times 1. So what is this? I guess I can cancel my 3's. 1 over x minus 1 over x minus 2. Clean up some of that scratch work. And then, I don't know, I think I would do an LCD again. So I'm going to multiply this one by x minus 2. And this one by x. X minus 2 minus x over x by x minus 2. Negative 2 over x, x minus 2. Looks like that comes out pretty nice. Okay, what about number 7? Derivative of ln of x over e to the 2x. Okay, so this is a little different because you see how in this last one here, you see how inside the log I had a quotient? Down here, actually the only thing inside the log is the x, so I can't actually use a log property there. You see the difference? So let me see the other one if we can illustrate. So see how up here I had a product inside of the log, so I used a log property. I think the last one was the same. So again, I had a product inside of the log, I used a log property. With this guy, again, the only thing inside the log is the ln, or the x rather. So I can't actually use any log properties there. So actually here I would think I would use the quotient rule. So I go ahead and set up the derivative using the template for the quotient rule. Okay, derivative of the top times the bottom. Okay, derivative of the bottom, so let me see, the bottom here is e to the 2x. Remember the derivative of that? The derivative of the exponential is the exponential itself, but then times the derivative of the exponent. So it'd be 2 e to the 2x. And then I look at simplifying this. So I see in the top, I see a GCF. E to the 2x can come out. I'll have a 1 over x minus a 2 ln of x. And then in the bottom, what is that? Multiply e to the 4x. Clean this up. So actually I can cancel. Let's see. So I'd have 1 over x minus 2 ln of x. And then what would that leave me with? An e to the 2x? Oops. Like that. I mean, I don't know. Maybe an LCD, I guess, multiply this by x over x. Let's see what that gives me. 1 minus x ln x over x e to the 2x. That looks good to me. Wait a minute, I think I missed one thing. Let me double check here. Okay, I have my 1 over x. Let me add one more step. Make sure I got everything right. So what did I do here? Let's see, I had 1 over x. I should have minus 2x ln x over x over e to the 2x. So I think, let's see, what am I missing over here? Missing a 2. 1 minus 2x ln of x, and then the x goes down with the e to the 2x. Okay, now I think I got it right. Okay. All right, so what else do we have? So here's an interesting one. So in this guy, well, here's an interesting idea, because see how I have a product here? 3 different factors multiplying together. So I guess I could use, you know, the quotient rule, the power rule, the chain rule, or rather, I mean, I could use the product rule, then here the power rule, then here I guess I'd use the product rule twice, here I'd use the chain rule somewhere in there. So I mean, I could do that, but it would be kind of long. So there's another idea now that we know how to work with derivatives of logarithms. And the other idea would be to use something called logarithmic differentiation. So you see how this function actually doesn't have any logarithms in it as it's written? But what if I take the log of both sides? I mean, when I say log, I'm thinking specifically of the natural log. So should I say that then? Take the natural log of both sides. Okay, so what would happen if I do that? So let's see. So I mean, I guess I could start out by saying this is the same as a y equals, right? So if I take the ln of both sides, it just looks like this, yeah? But you see, now I have these products inside of that logarithm. So can't I use this rule again, where I have multiplication inside of a log? I can break that up and it's a sum. So again, so far I'm just manipulating the function. So I have ln of y, the ln of x squared, plus ln of x minus 3, plus ln of x squared plus 2. So maybe should I put up here in the instructions? What did I do here? I used this logarithmic differentiation by taking the log of both sides, simplifying from there. So now let me take the derivative of both sides. So I'm going to find d dx of this side and d dx of this side. So on the left side here, I have to be careful. I'm actually using an implicit differentiation because I go, okay, derivative of ln of y is, well, 1 over y. But then remember, I have to multiply by the derivative of the inside. So wouldn't that be dy dx, the derivative of y? Y is a function of x, right? Okay, what about on the right side? Okay, derivative of ln of x squared, so 1 over the argument times the derivative of the argument. And then again, derivative ln of x squared plus 2, so 1 over x squared plus 2 times derivative of the argument. So what is that? 2 over x plus 1 over x minus 3 plus 2x over x squared plus 2. Okay, now remember, I'm trying to find dy dx. So I guess I have to multiply both sides by that y then, right? So dy dx, let's see, I have 2 over x plus 1 over x minus 3 plus 2x over x squared plus 2 times y. But then I really don't want to have that y in the answer. I really just want to have x's in the answer. But actually, can't I take care of that easily? Because look, see how up here, here's y, right? That's the original function, isn't it? So wouldn't I just replace the y then by that function? So let's see what that would look like. That would be x squared, x minus 3, x squared plus 2. Actually, this is going to turn out nice because look at the denominators. So when I multiply this through, look, when I multiply to that first factor, well, an x cancels. So what will that leave me with? That'll leave me with a 2x, x minus 3, x squared plus 2. When I multiply here, my x minus 3's cancel. So I'll have a 1 times an x squared and an x squared plus 2. Put 1 in there or not. And then here. This guy cancels. And so I'd have a 2x and then an x squared and an x squared plus 2. Oops, I think I made a mistake in the last one. So as I'm going through here, I'm always double checking. So I don't know, should I clean this up a little bit? We can double check this last step together. Let's clean this guy up. I'm just checking everything. Okay, so when I multiply this through to the first factor, let's make sure I got everything right. So I'd cancel out an x. So then I would have, let's see, I'd have my 2, that's here. I'd have from this guy an x minus 3, x squared plus 2. That looks okay to me. Okay, let me clean up again. And then, so now, taking all of this, distributing it here. So here my x minus 3 would cancel. So I'd have my 1, I'd have my x squared, and my x squared plus 2. That looks okay. So then here's where I think I saw a mistake, distributing to the last term. Okay, so I'd have my 2x, looks good. My x squared looks good. I'm okay, I'm all right, thank you. Let me double check this one again. Okay, so I was 2x times x squared looked okay. And then I think my mistake was my x squared plus 2 canceled with my x squared plus 2, and I should have had here, that should be an x, oops, and x minus 3. So that one's a little bit more interesting. And I think we could even leave that there. All right. What about find the equation of the tangent line? All right, we've done a bunch of this. All right, so I guess first thing I'll need is the derivative. It's a chain rule. So 1 over x squared times 2x. It's just 2 over x, that's an easy one. Okay, what about f prime at the value 2? Also easy, huh? So what is that? That's the slope of the tangent line at x equals 2. Okay, so then I'm looking for a y equals mx plus b. I know the slope is 1. Now I have to plug in the point. Okay, so my point interest was 2. Guess I need f of 2. So the original function was ln of x squared. So that'd be ln of 4. Okay, so that's what? ln 4. So I guess b would be ln of 4 minus 2. Now I can't combine that 4 and the 2 because the 4 is inside the ln and the 2 is not. So then this guy goes in for my b, and then I guess I'm done. So that would be the equation of the tangent line. Okay, where is f of x increasing, decreasing? Well, we already found the derivative. Let me write that down here. What was it? 2 over x? Okay, so I would just set up my sign chart. Let's see. All right, so f prime of x. So there are going to be no values where the derivative is 0. So no extrema, no local extrema. But f prime of x does not exist at x equals 0. Let me look back at the original function. Where are we here? Lost track, 0. Okay, so looking back at the original function here, I can see the original function is also undefined at 0. I can't take the ln of 0. So, I mean, that just means that we technically wouldn't say that 0 is a critical number. However, 0 is still where something interesting happens. So I still need to include that in my sign chart as far as determining where the function is increasing or decreasing. Okay, so let me say, okay, what about f prime of a big number, right? If I plug a big number in here, it's positive, yeah? Versus if I plug a negative number in here, it's negative. Okay, so I can make my conclusion. And then, of course, I didn't ask, but there were no critical numbers, no places where the derivative was 0, so there would be no local extrema. We mentioned that. And one more. Find the intervals of concavity and any inflection points. So I guess if I see concavity, I know I'm thinking I need, keep losing my place there. If I'm looking at concavity, I know I'm looking at the second derivative. Okay, so first derivative, I see a product. Okay. So 2x ln of x. 1 over x squared. I think we did one very similar to this. Maybe it was even the same one. Factor out the x if you like. Either way. Okay, but I need the second derivative. Oh, I don't know. I could use either form. Kind of looking at, let's use this one. Okay. Yeah, actually, I think I'm going to go with the other one. Either way, I'm going to need the product rule. So let me use this guy. I'm going to need the product rule. So set up another product rule template. Okay, derivative of x is 1, 2 ln of x plus 1. And then the derivative of 2 ln of x is 2 times 1 over x, like so. don't know what I keep hitting there. Where are we? Here. 2 ln of x plus 1 plus 2. So 2 ln of x plus 3. Looks like my second derivative. Okay, so then as far as intervals of concavity or, potential inflection points, I have to look at setting that second derivative equal to 0. Okay, remember, ln of x is log base e of x, right? So here I need another log rule changing to exponential form. What section was this in? 5.2? 5.2. So that would be x equals e to the negative 3/2. Okay, should I simplify that? So that's 1 over e to the 3/2. And what if I write that as a radical? 1 over the square root of e cubed. So there's my number, my potential inflection point. And so once I have my x value here, I set up my sign chart, and again, I'm thinking about the second derivative. So my second derivative, right, looks like this. I'm kind of thinking, okay, so what's one way to figure out whether that guy's going to be positive or negative on, the left and right side here? Because it's a little bit hard to figure out what the value of 1 over square root of e cubed is, say, without a calculator. So I'm just kind of thinking if I could figure this out without actually plugging values in. Like, just think about this guy for a second. What does ln of x look like if I was to graph it? Do you remember that? It looks like this, doesn't it? Okay, what does this 2 do? That's a vertical stretch, right? Multiplies the y's by 2, but I have same kind of a basic shape. Something like that, say. And then up 3. So if I was to actually graph that guy, of course, very rough sketch, look something like that, say. But the interesting part is, look, I mean, when we set this equal to 0, we found the x-intercept, right? It was this value. So actually, can't we already tell what happens? You see how on the right side of that x-intercept, the function's positive, right? Versus to the left there, the function's negative. So look back up here. Can't I actually then make a conclusion already there? So I should be able to write out a conclusion then. Let's clean this up a little bit. Concave down. And cave up. Okay, and then what about inflection points? I do have a point where the graph changes concavity. So let me circle this. Right in inflection point. So I can clean some of this up. Alrighty, so I had 1 over square root of e cubed. And then I have to plug that value in the function itself. Where the heck was the function? The function was up here. So I'd have x squared ln of x so that would be 1 over e cubed. And then that's ln of e to the negative 3/2. This can come down. And then ln of e is 1, right? So that's kind of a long problem, huh? All right, so finally have my inflection point. So I guess I have all the information.